Hello dear students, I am Samir Velankar. I welcome all of you to this video on second normal form. In the previous video, we saw that every table in DBMS is always in first normal form because it is flat table, that is every attribute in that table is atomic. It is neither multivalued nor it is composite. Now, what is second normal form? Check that the table is said to be in second normal form if it does not have any partial dependencies. Check this word, partial dependencies. We already know what is known as functional dependency. Now, what is meant by partial dependency would be understood by using an example. Just check if the table does not have any partial dependencies, then the table is said to be in second normal form. Now, as an example, just check that we have a table R with attributes ABC, three attributes, and the functional dependencies defined on this table is AB together determines the value of C and B determines the value of C. Now, all of you know from the past videos that how do you find candidate key using this FD set? How do you find candidate key? Using the FD set, you find attribute closure. Now, who can be the candidate key of this table RABC? You recall the trick given in that video where we saw lot of examples on finding candidate key using FDs, that is functional dependencies, is that see all the functional dependencies and just check which attribute is not appearing on the right hand side of any FD. Now watch, C appears on the RHS. Here it appears in the first FD and here it appears in the second FD. That's the only two functional dependencies we are having, and in both C appears on the right hand side. But what does not appear is neither A appear nor B appear on the right hand side of any FD. Then surely the candidate key must contain A and B. I repeat, the candidate key must contain A and B. Now, what other keys it might contain, we don't know. But candidate key cannot be without A and B. A and B must be there because A and B is never there on the right hand side of any FD. So what we do is, we first of all check is AB the candidate key. How do you find it is by finding AB closure? Now AB closure will surely contain A and B. Definitely you know what is closure by this time. And now because AB is there, both are there in this particular closure, you note this functional dependency AB together can bring C, even alone B can bring C and B is there in this FD set. So C also joins this closure. Now you observe there are only three attributes of this table ABC and AB can determine all three attributes ABC. That means AB is the candidate key of this particular table. I hope you got that. I am sure it is expected that you know what I am talking about. When I am discussing about the second normal form, I have discussed who is the candidate key, and I hope you have watched the videos in the correct sequence. The candidate key of this table is AB. But the question is, are there any more candidate keys? Now, how do you answer this question? Who knows? BC might be the candidate key. That means BC can also determine ABC. That means when you find BC closure, it might contain ABC. That means BC is capable of determining all the attributes of the table. So who knows? B and C together form a candidate key. Or is it that only AB is the candidate key of this table and there are no more candidate keys? Now have a look at this. Candidate key must contain A and B. Why? Because in none of the right hand sides of none of the FDs, A and B exist. So whatever is the candidate key, AB must be the part of the candidate key, isn't it? And now you cannot add anything to this because if you add anything to this, it will be a super key. Come on, AB already is the candidate key. What's the point in asking is ABC a candidate key? It is supposed to be candidate key. In fact, ABC will determine all the attributes. we will say ABC is a super key. That means one possibility, you cannot remove A and B from the candidate key. Correct? A and B have to be there in the candidate key. And secondly, you can't add anything to this because then it will be super key. So AB is the only candidate key of the given table. Now watch this. For the given table RABC, the candidate key is AB because AB plus is closure of this is ABC. So all the attributes are there in AB closure. So A and B have the capability to determine all the attributes. So AB is the candidate key. Now have a look at the dependency which I am ticking. This BC, B determines C. This FD, B determines C, is partial dependency. That's the word which came in the definition of second normal form. B determines C is partial dependency because the left hand side of this dependency is subset. Left side of this dependency is subset of candidate key. Who is the candidate key? AB. Then isn't this B left hand side part of the candidate key? It's not complete, it's part. So left hand side of this dependency is the part of the candidate key, subset of the candidate key. Wait, there is more to come. And the right hand side of this dependency, this is also very important. The right hand side is C, which is not the part of the candidate key. We call such attributes like C, which are not the part of candidate key, as non-prime attributes. Come again. Who is the candidate key? AB. AB. Correct? Then A is prime attribute. B is prime attribute. Any attribute which is part of the candidate key, is called prime attribute. But C is not the part of candidate key. Then C is a non-prime attribute. Non-prime. Now what is the dependency you have? B determines C. Now have a look at left hand side. Isn't this B subset of AB, which was the candidate key? So B is a prime attribute, but we don't have the complete candidate key on the left hand side. We have subset of the candidate key, that is B. And more to come is right hand side C is a non-prime attribute. So we say whenever a prime attribute determines a non-prime attribute, check the words very carefully. Whenever a whenever a prime attribute determines a non-prime attribute, and the prime attribute, this left hand side, prime attribute is subset of candidate key. So it's not that suppose candidate key is AB, then here we have written only B. So it's subset of AB, determines C, but C is a non-prime attribute. It is not the part of the candidate key. Then we call this as partial dependency. Okay, look at the first dependency. First dependency, AB determines C. Is this partial? Check, I am writing it again over here. AB determines C. What's the left hand side? Is perfect candidate key. It is not the subset of candidate key. AB is the candidate key and the left hand side is the candidate key, isn't it? What is the right hand side? It is a non-prime attribute. C is not an attribute which forms the candidate key. But this is not partial because left hand side is a complete candidate key, isn't it? So what is partial dependency? Left hand side may be part of the candidate key, and right hand side may be a non-prime attribute. So whenever part of the candidate key determines a non-prime attribute, it is known as partial dependency. So this is not partial, but this is partial. So as this table ABC with three attributes ABC has a partial dependency, I'll write it as PD. This table is not in second normal form. I hope you are understanding. Due to this partial dependency, we say this table is not in second normal form. So we have to bring it in the second normal form. So how do you bring this table into second normal form? is by removing that partial dependency. Table should not have partial dependency, isn't it? Only then it is in second normal form. So we will have to remove that partial dependency. So what we do is, just don't read the table that I have drawn right now over here. We will see what it is. What we do, which two dependencies we have, I am writing again. AB determines C. This is fine. This is not partial because left hand side is complete candidate key. Second is B determines C. Look, left hand side is part of AB and right hand side is a non-prime attribute. This is partial dependency. Then what we do is we find B plus. We find closure of the left hand side of the partial dependency, and B closure, observe, will definitely contain B. And from the given FD set, of course, we will find closure using only given FD set. From the given FD set, B will bring in C because B determines C. And now nothing else will be brought in. This AB determines C is not going to bring in anything new. Then B plus, B closure contains BC. So what we do is check these are the attributes of our original table ABC. Then we say B, you better take away C. Check the working. B will take away C. So hence there will be a table, let's name it as R2, which will have B and C. And now the other attributes which are pending. See, B has taken away C. So I have striked out C and B has taken away C. So BC have been written in one of the tables. But whatever remains now, A and B will be in the other table. So R1 will contain A and B. I'll show this working again over here. ABC is the original table and B determines C is the partial dependency. So we have found B plus because B was determining C. So we found left hand side closure B plus. B plus contains BC. So one of the tables will contain BC, these two attributes. Let's call it as R2. And we say B closure contains C. So B has taken out C. This is the way we show. Now in the other table remaining, these two attributes A and B will go. So these are the two tables that we will get. Now observe, just observe that these two tables, these two tables have common attribute B. Remember lossless, remember we have decomposed this table into two different tables, but the decomposition has to be lossless. So what do you remember? There should be a common attribute. Okay, R1 and R2 are having common attributes, that is B, and that common attribute has to be, remember, has to be a candidate key in one of the tables. Now observe here B determines C is applicable. From the original FD set, B determines C is applicable over here. So B can determine all the attributes in R2. So B is the candidate key in R2 and it is a common attribute. So it is lossless, isn't it? So these are the two tables we make. Now let's not stop here. Watch it. Watch it over here. Definitely this decomposition is lossless, but we have to see, does R1 have any partial dependencies and does R2 have any partial dependencies? Now one of the dependency which is applicable over here is B determines C, and notice it is not partial because the left hand side is the candidate key. B is the candidate key of R2 and right hand side is a non-prime attribute, but perfectly candidate key is determining a non-prime attribute. So this is not partial. And what about this? Here, we don't have a candidate key because from the given FD set, AB determines C. Now, AB determines C is not applicable here. Why? Because C is not there in R1. Now, when there are only two attributes called AB, we can say AB determines AB. AB itself is the candidate key over here. What that means is, surely this also does not have any partial dependency, correct or not? Or you can say no such dependency is there from the given table, isn't it? We don't have A determines B or B determines A. So there is no problem with this table which contains AB, and there is no problem with this table either because this does not have any partial dependency. Come again, if you have any partial dependency, what will you do? Just check this. We have this partial dependency in this table, B determines C, correct? What did we do? We simply find B plus, and B plus had B and C. So what we did is, out of ABC, let BC be in one of the table, correct? So we created a table R2 which had BC, and now we want a common attribute. We said B took away C with it. Now AB remains and AB goes in the other table. This will give us the two tables in 2NF, second normal form. Isn't it so? Now, before we close this discussion, watch. What was the problem with R1, which had two dependencies? AB determines C was the first dependency and B determines C was the second. Now I hope you remember definition of B determines C. It means in two tuples T1 and T2, if value of B is same, then in those two tuples T1 and T2, value of C should be same. Correct or not? Don't forget that fundamental. Now you watch in these three tuples, value of B is same, B1, B1, B1. Then value of C has to be same, isn't it? C1, C1, C1. And just check in these three tuples, value of B is same, B2, 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 then value of C has to be same, that is C2. Don't you see bulk of redundancy over here? This is too bad. I mean, suppose this was a name of a town and this was the name of state. C was the name of state. Just imagine. Just imagine B was name of a town, B was name of a town, and C was name of a state. And if I say that B1 is Mumbai, actually city, I'm so sorry, it's okay. Mumbai, then state Maharashtra. Now, if this second person is also from Mumbai, this is so ridiculous to store Maharashtra again and again. I hope you're understanding, isn't it? This is a lot of redundancy. And definitely, if two tuples have Mumbai, then those two tuples must have Maharashtra. Mumbai won't move out of Maharashtra, isn't it? So this is redundancy. This is what B determines C has. And this is partial dependency because AB together is the candidate key and now B alone determines C. Part of the candidate key is determining non-prime attribute C. So this is redundancy. So what is the best remedy for this? What you can do is you can create two tables. Now the two tables over here are A, let A and B be in one of the table and B and C be in the other table. Now watch, we had B1 and B2, isn't it? Watch the original table. Unique values of B were B1 and B2. And what is the value for B1? It is C1. And what is the value for B2? It is C2. That means you don't have to again and again store that Mumbai is located in Maharashtra. Come on, if Mumbai is in Maharashtra, store it only once in this R2 table. And now in R1, you will say A1, say person. This A1 is a person. You are from B1. Okay, A2, you are also from B1. A3, check. A3 is also from B1. Fine. You might say, sir, but this is redundancy. You are storing B1 over here. Fine, I agree. Somewhere you will have to store that Samir is from Mumbai, Ravi is from Mumbai, Arun is from Mumbai. But Mumbai is in Maharashtra. Come on, Mumbai is in Maharashtra can be stored only once. That is what we have reduced the redundancy. That B determines C was creating tremendous amount of redundancy. So to continue, A4 is from B2 and A5 is also from B2 and A6 is from B2. But you note, we have not stored C1, C1, C1 so many times and we have not stored C2, C2, C2 so many times. In our R2 table, the redundancy has got dropped. I hope you have understood the discussion over here, found it very interesting. I promise in the next video, we will see lots and lots of example. We will be seeing a table from our next video onwards. We will be seeing a table and FDs and we will say, good Lord, this is not in 2NF. Then we will bring it in 2NF and we will justify that this is in 2NF. Thank you very much.